In mathematics, an isomorphism is a homomorphism that admits an inverse. Two mathematical objects are isomorphic if an isomorphism exists between them. An automorphism is an isomorphism whose source and target coincide. The interest of isomorphisms lies in the fact that two isomorphic objects cannot be distinguished by using only the properties used to define morphisms. Thus, isomorphic objects may be considered the same as long as one considers only these properties and their consequences. For most algebraic structures, including groups and rings, a homomorphism is an isomorphism if and only if it is bijective. In topology, where the morphisms are continuous functions, isomorphisms are also called homeomorphisms or bicontinuous functions. In mathematical analysis, where the morphisms are differentiable functions, isomorphisms are also called diffeomorphisms. A canonical isomorphism is a canonical map that is an isomorphism. Two objects are said to be canonically isomorphic if there is a canonical isomorphism between them. For example, the canonical map from a finite-dimensional vector space V to its second dual space is a canonical isomorphism. On the other hand, V is isomorphic to its dual space but not canonically in general. Isomorphisms are formalized using category theory. Imorphism f x y in a category is an isomorphism if it admits a two-sided inverse, meaning that there is another morphism g y x in that category such that gf equals 1x and fg equals 1y, where 1x and 1y are the identity morphisms of x and y, respectively. Examples: logarithm and exponential. Let be the multiplicative group of positive real numbers, and let be the additive group of real numbers. The logarithm function satisfies for all, so it is a group homomorphism. The exponential function satisfies for all, so it too is a homomorphism. The identities and show that and are inverses of each other. Since is a homomorphism that has an inverse that is also a homomorphism, is an isomorphism of groups. Because is an isomorphism, it translates multiplication of positive real numbers into addition of real numbers. This facility makes it possible to multiply real numbers using a ruler and a table of logarithms, or using a slide rule with a logarithmic scale. Integers modulo 6. Consider the group, the integers from 0 to 5 with addition modulo 6. Also consider the group, the ordered pairs where the x-coordinates can be 0 or 1, and the y-coordinates can be 0, 1, or 2. Where addition in the x-coordinate is modulo 2 and addition in the y-coordinate is modulo 3. These structures are isomorphic under addition, if you identify them using the following scheme: 0, 1, 2, 3, 4, 5, or in general mod 6. For example, note that plus equals, which translates in the other system as 1 plus 3 equals 4. Even though these two groups look different in that the sets contain different elements, they are indeed isomorphic. Their structures are exactly the same. More generally, the direct product of two cyclic groups and is isomorphic to if and only if M and N are coprime. Relation-preserving isomorphism if one object consists of a set X with a binary relation R and the other object consists of a set Y with a binary relation S. Then an isomorphism from X to Y is a bijective function f x y such that S is reflexive, irreflexive, symmetric, antisymmetric, asymmetric, transitive, total, trichotomous, a partial order, total order, strict weak order, total preorder, an equivalence relation, or a relation with any other special properties, if and only if I is. For example, R is an ordering and S an ordering, then an isomorphism from X to Y is a bijective function f x y such that such an isomorphism is called an order isomorphism or an isotone isomorphism. If x equals y, then this is a relation-preserving automorphism. Isomorphism versus bijective morphism. In a concrete category, such as the category of topological spaces or categories of algebraic objects like groups, rings, and modules, an isomorphism must be bijective on the underlying sets. In algebraic categories, an isomorphism is the same as a homomorphism, which is bijective on underlying sets. However, there are concrete categories in which bijective morphisms are not necessarily isomorphisms, and there are categories in which each object admits an underlying set but in which isomorphisms need not be bijective. Applications. In abstract algebra, two basic isomorphisms are defined: group isomorphism, an isomorphism between groups; ring isomorphism, an isomorphism between rings. Just as the automorphisms of an algebraic structure form a group, the isomorphisms between two algebras sharing a common structure form a heap. Letting a particular isomorphism identify the two structures turns this heap into a group. In mathematical analysis, the Laplace transform is an isomorphism mapping hard differential equations into easier algebraic equations. In category theory, i.e., the categories C consist of two classes, one of objects and the other of morphisms. Then a general definition of isomorphism that covers the previous and many other cases is: an isomorphism is a morphism F, a B that has an inverse, i.e., there exists a morphism G, BA with FG equals 1B and GF equals 1A. For example, a bijective linear map is an isomorphism between vector spaces, and a bijective continuous function whose inverse is also continuous is an isomorphism between topological spaces, called a homeomorphism. In graph theory, an isomorphism between two graphs G and H is a bijective map F from the vertices of G to the vertices of H that preserves the edge structure, in the sense that there is an edge from vertex U to vertex V in G if and only if there is an edge from F to F in H. See graph isomorphism. In mathematical analysis, an isomorphism between two Hilbert spaces is a bijection preserving addition, scalar multiplication, and inner product. In early theories of logical atomism, the formal relationship between facts and true propositions was theorized by Bertrand Russell and Ludwig Wittgenstein to be isomorphic. An example of this line of thinking can be found in Russell's Introduction to Mathematical Philosophy. In cybernetics, the good regulator or Conant-Ashby theorem is stated: every good regulator of a system must be a model of that system. Whether regulated or self-regulating, an isomorphism is required between regulator part and the processing part of the system. Relation with equality. In certain areas of mathematics, notably category theory, it is valuable to distinguish between equality on the one hand and isomorphism on the other. Equality is when two objects are exactly the same, and everything that's true about one object is true about the other, while an isomorphism implies everything that's true about a designated part of one object's structure is true about the others. For example, the sets and are equal, they are merely different presentations, the first an intentional one, and the second extensional, of the same subset of the integers. By contrast, the sets A, B, C, and 1, 2, 3 are not equal. The first has elements that are letters, while the second has elements that are numbers. These are isomorphic sets, since finite sets are determined up to isomorphism by their cardinality, and these both have three elements. But there are many choices of isomorphism. One isomorphism is while another is, and no one isomorphism is intrinsically better than any other. On this view and in this sense, these two sets are not equal because one cannot consider them identical. One can choose an isomorphism between them, but that is a weaker claim than identity, and valid only in the context of the chosen isomorphism. Sometimes the isomorphisms can seem obvious and compelling, but are still not equalities. As a simple example, the genealogical relationships among Joe, John, and Bobby Kennedy are, in a real sense, the same as those among the American football quarterbacks in the Manning family. Archie, Peyton, and E. The father-son pairings in the elder brother-younger brother pairings correspond perfectly. That similarity between the two family structures illustrates the origin of the word isomorphism. But because the Kennedys are not the same people as the Mannings, the two genealogical structures are merely isomorphic and not equal. Another example is more formal and more directly illustrates the motivation for distinguishing equality from isomorphism. The distinction between a finite-dimensional vector space V and its dual space V** equals phi vk of linear maps from V to its field of scalars k. These spaces have the same dimension, and thus are isomorphic as abstract vector spaces, but there is no natural choice of isomorphism. If one chooses a basis for V, then this yields an isomorphism for all u VV. This corresponds to transforming a column vector to a row vector by transpose, but a different choice of basis gives a different isomorphism. The isomorphism depends on the choice of basis. More subtly, there is a map from a vector space V to its double dual V** equals x V** k that does not depend on the choice of basis for all V and phi V**. This leads to a third notion, that of a natural isomorphism. While V and V** are different sets, there is a natural choice of isomorphism between them. This intuitive notion of an isomorphism that does not depend on an arbitrary choice is formalized in the notion of a natural transformation. Briefly, that one may consistently identify, or more generally map from, a vector space to its double dual for any vector space in a consistent way. Formalizing this intuition is a motivation for the development of category theory. However, there is a case where the distinction between natural isomorphism and equality is usually not made. That is for the objects that may be characterized by a universal property. In fact, there is a unique isomorphism, necessarily natural, between two objects sharing the same universal property. A typical example is the set of real numbers, which may be defined through infinite decimal expansion, infinite binary expansion, Cauchy sequences, Dedekind cuts and many other ways. Formally, these constructions define different objects, which all are solutions of the same universal property. As these objects have exactly the same properties, one may forget the method of construction and considering them as equal. This is what everybody does when talking of the set of the real numbers. The same occurs with quotient spaces. They are commonly constructed as sets of equivalence classes. However, talking of set of sets may be counterintuitive, and quotient spaces are commonly considered as a pair of a set of undetermined objects, often called points, and a surjective map onto this set. If one wishes to draw a distinction between an arbitrary isomorphism and a natural isomorphism, one may write for an unnatural isomorphism and for a natural isomorphism, as in VV** and VV***. This convention is not universally followed, and authors who wish to distinguish between unnatural isomorphisms and natural isomorphisms will generally explicitly state the distinction. Generally, saying that two objects are equal is reserved for when there is a notion of a larger space that these objects live in. Most often, one speaks of equality of two subsets of a given set, but not of two objects abstractly presented. For example, the two-dimensional unit sphere in three-dimensional space and the Riemann sphere, which can be presented as the one-point compactification of the complex plane C, infinity, or as the complex projective line, are three different descriptions for a mathematical object, all of which are isomorphic, but not equal because they are not all subsets of a single space. The first is a subset of R3, the second is CR2 plus an additional point, and the third is a subquotient of C2 in the context of category theory. Objects are usually at most isomorphic. Indeed, a motivation for the development of category theory was showing that different constructions in homology theory yielded equivalent groups. Given maps between two objects x and y, however, one asks if they are equal or not, hence equality is the proper relationship, particularly in commutative diagrams.